to the amount of Q still on the plates. So in other words, when the amount of charge you still have on the plates is pretty high, the rate at which they want to get off is really high. They'll flow off very rapidly when there's a lot of them still on there. And likewise, when the amount of charge that's still on the plates gets very small, well then the rate at which they want to get off is also a trickle at that point. Okay? So it happens first very rapidly, and then it slows down over time. Okay? Until when the last couple stragglers of charge flow off, it's a pretty lazy process at that point. Okay? Now, the rate of something, when it's proportional to the amount of something, any time that that happens, the mathematical consequences, which if you've never taken calculus, you'll just have to believe me, but any time the rate at which something happens is itself proportional to the amount, you get an exponential. Okay? This, something like this, whenever the rate is proportional to the amount itself, you get an exponential, which hopefully you, or I'm sure you have seen at some point in your math class. That is basically the mathematical manifestation of that. So it's a curved function which drops off steeply at first and then gradually flattens out. You guys have seen these at some point? Okay. Now, I cannot do the derivation of the equations from first principles because there's calculus involved. And so what I'm going to do is I'm going to give you the bare minimum that we need to borrow from higher mathematics. I'm going to give you the current function and the charge function. Once I do that, we can find all the other functions. Okay? So I'm going to give you two functions. These are on your equation sheet. You just grab them and use them. You don't need to know where they come from, but you should understand the conceptual ramifications of them, how to manipulate them mathematically, and how to use these functions to be able to leverage them to get any other function. So I'm going to show you all that right now. So first of all, let me remind you of just the bare properties of an exponential. So if you see something like this in math class, this is just totally math class, but this is some of the more advanced mathematics that I need you to be able to do. So I'm just going to take 5 minutes to make sure we're all on the same page. So let's check it first. At x equals 0, we get y equals e to the minus 0. Well, anything to the 0 is what? 1. Okay? Don't ask me about 0 to the 0, but anything else to the 0 power is 1. Okay? And when x is equal to infinity, some very large number, we get y equals e to the negative infinity, or if you prefer putting in the denominator, there again, it's not important that it's e. Any number to the infinity power is a massive number. And since it's the denominator, what is this basically equal to? 0. Okay? So we have that the extremes of this function, we have that it starts at 1, and then it actually is going to curve and eventually approach 0. Now, that is what it looks like even if it's not e. If you replaced e with 7, it would still basically have that general shape. The exact curvature would be different, but it's basically still like 7 to the 0 is still 1, and 7 to the negative infinity is still 0. Okay? So we have not yet actually used the properties of the exponential at all. This is just anything to the minus x power. So let's plug in x equals 1 to get an intermediate point. So this is y equals e to the negative 1, or 1 over e. So e is a special number in mathematics. It's just like pi. It's a transcendental number, 2.7, and then just keeps going on and on. Never repeats, never ends. Okay? Just keeps going. If you want to impress your friends that you know that many digits, if you can remember 2.7, it repeats 1828 twice, and then 45, 90, 45 triangle. Okay? For our purposes, it's basically a number just shy of 3. Okay? So it's 1 over e is about a third. Okay? It's not quite 3, so it's not quite a third. It's 0.37. Okay? So we don't really care about keeping things exact in physics. We just crunch it down to a decimal. Okay? So what that tells us is that when we've reached a value of 1, we have reached a value of 0.37 over here. Now, 0.37, we can also think of it like this. If we start off at 1 and now we're at 0.37, well, it means that we're at 37% of the value we started with, which of course means we've lost 63%. Okay? So this is a very commonly used benchmark when you're working with exponentials. Okay? When you have gotten to this point, you are at the 63-37% benchmark. Okay? So that's a little bit about just exponential functions. And our functions are basically going to be that exact function with a few bells and whistles. So let's take, for instance, the charging function. If we write, what does the charge look like as a function of time? Well, one of the first obvious things we need to do to fix our kind of bells and whistles we need to put on our function, we can't have that it always starts at 1, right? That's like saying every single discharging starts from 1 coulomb. Why would it always be 1 coulomb? It's whatever amount of charge you put on the capacitor. And so multiplying it by Q initial makes sure that it starts at Q initial. It makes sure that the charging starts from the actual amount of charge you have to begin with, not just 1 coulomb, which is what it would be if you left the exponential in its completely raw form. Then, as it dies off over here, it's going to turn out that how fast or how slow this proceeds, it really depends on what your circuit is like. So it'd be really weird if after 1 second, every circuit hit that same benchmark 63-37%. So instead, that's where we use in the numerator, we use this thing called tau. So if you take into your function, if you plug in t equals tau, oh, that brings me another point. You guys know that this is a function of, right? This is not q times t? Yes? So this is not, again, this is not q times t. This is q is a function of t. Okay? So if I plug in t equals tau, then I get minus tau over tau. And that's, of course, q e to the minus 1, or q initial over e, or, as we said, 0.37 of q initial. So tau is how we get to move this benchmark around. So after t equals tau, what that represents is the time it takes to get to 37% of your initial value because you've already dropped 63%. So we basically have those two features in our equation which allow us to kind of manipulate, stretch it on both axes. So the Q initial is what allows us to make sure we start off with the right value on the vertical axis. And then the tau is what allows us to stretch the, you hit the 63.37% benchmark to wherever it would be appropriate on the horizontal axis. Okay? So what is tau? Tau is the time it takes to get to the 63.37% benchmark. It's the way that we judge one circuit against another. So first of all, you might say, that's an odd benchmark. Why don't we just ask what's the time it takes to lose all its charge? Well, here's the problem. No matter what the circuit is, if it's an exponential, the amount of time it takes to lose all of its charge is always infinity. That's an exponential. It doesn't actually go to 0 until it gets to infinity. Okay? So that would be the answer for every circuit. And again, the reason why is that once you have a minuscule amount of charge left, the rate at which it will drain off is minuscule as well. So the charge will kind of really never, ever really get off there. At some point, it might even drop below detectable levels, but the charge will never really perfectly flow off there. So we can't use the time it takes to discharge completely, because every circuit, the answer is t equals infinity. So then you might say, well, let's just say how much time does it take to drop halfway? That's like more intuitive, right? 50%. 50-50, right? Except for in the exponential land, 50-50 is actually not very convenient. So our benchmark is the 63.37% benchmark, because that's very natural for an exponential. It actually comes from the fact, when is the initial value cut by e? So when is the initial value? It's now divided by e from whatever it was at the beginning. So that is our baseline for judging things. And as long as we agree that that's our benchmark, as weird as it is when you look at it as a percentage, as long as we judge all circuits by this same benchmark, we can tell if one takes longer or shorter. Okay, so for instance, if we had another circuit which had a larger tau value, let's say this second circuit, tau 2, that would look like this. It also starts at the same initial charge. It also takes forever for the charge to leak off completely. But if you compare at any given time, the green line is always higher than the black line, right? So at any given time, it's always more full, not as much as flowed off. And so it takes longer to get to this benchmark. The charge flows off slower, and so it takes longer to get to t equals tau. It takes longer to hit this benchmark that we've agreed to judge all circuits by. So let me tell you what goes into tau. You can actually predict whether it will take longer or shorter amount of time to hit this benchmark by looking at the properties of the circuit. All you have to do is multiply the resistance times the capacitance. That's why we call these RC circuits, by the way, because R times C literally appears in the equations. Believe it or not, if you work out the units of capacitance and times resistance, so that'd be ohms times farads, that actually works out to a second. So next time someone asks you what was the winning time on the 100-meter dash on the Olympics, you can say it was like, I don't know, about 10 ohm farads, okay? It's equivalent to a second, okay? So let's talk about why these should affect your benchmarks. First of all, this seems to indicate that if your resistor that you're discharging through is larger, it'll take longer to hit this benchmark, okay? Now, does that make sense conceptually? You're discharging through a larger obstruction, right? It's harder to do that. So you have your discharge through a larger obstruction Therefore, it takes longer to hit the benchmark. Okay? So if the resistance that you're discharging through is twice as much, it'll take twice as long to get to this benchmark. Also, if your capacitance that you are discharging from is larger, that also increases tau. Let's talk about why that makes sense. Well, a larger capacitor is a more effective storage device. It can hold charge more easily. They're not crammed in there all against their will. There's lots of room to spread out. They're not that bothered being near each other, so the flow off the larger capacitor is going to be more casual. It's not going to be so rushed. Okay? So this is, it discharges from a better storage device. So the analogy is like a walk-in closet, this nice big capacitor, very good storage device, versus, say, I talked about last time, a small capacitor would be like one of those tiny closets, right? You open it up and the clothes practically fly out at you, right? Because you crammed them all into a small space, okay? So again, if the storage device itself is better, then the flow will not be quite as urgent, okay? So those are the two things you need to know to figure out how long it takes to hit this benchmark that we've agreed upon, the 63-37% benchmark. You need to know the resistor that you're discharging through and the capacitance you're discharging from. Okay? So in my example over here, this green line, where I had tau 2, and the amount of charge was always above the black line, the reason why that might be discharging slower is because it's discharging through a larger resistor, it's discharging from a better capacitor, or maybe both, right? As long as the R times C multiplies to a larger value, it'll have a larger tau. Are there any questions on that? Yeah?
In that case, Q initial is the same? Is that always the case?
Not necessarily, but I wanted to not have too many different control variables. So the Q initial would be the same if it was the same capacitor charged by the same voltage device, right? But so one example how these two might be different is that it's the same exact capacitor, exact same charging, but they're discharging through two different resistors. If the capacitances were different, the Q initial could still be the same, but you need to use different charging batteries to make that happen, right? Because generally speaking, if you take the same battery and apply it to do different capacitors, the bigger capacitor does a better job and stores more charge, and then Q initial wouldn't be the same. So I was just supposing that so that there weren't too many different things to consider. Are there any other questions? Okay, so that's the charging function that just kind of appeared out of thin air. You'll have to trust me that that's what the function is. I just want you to, of course, understand how to what it means. And then the current function is basically the same function. So just real quick, it looks like this, right? So we said that the current function, we already said that the current should be the largest at first, and then slow down to a trickle later, and it's the same type of exponential function. So all the same features. When t equals tau has passed, you've hit the 63-37% benchmark. So those are the two functions that I gave you, but from here, I don't need to give you any more because the rest of them you can find. You find them because you know the relationship that Q and I have to everything else. So just to give you an example, what if I wanted to find the voltage across the capacitor? Let's say I wanted to find the voltage drop across the capacitor as a function of time. Well, I just invert the formula, Q over C. So that's how you do it, right? We're leveraging the fact that as goes the charge, so goes the voltage. So if I know the charge is a function of time, I know the voltage is a function of time. All I have to do is throw in my function. That's what I get. And just to make it a little bit more spiffy, I might group the constants in front of the exponential. And then I can identify, what's that thing in parentheses there? Q initial divided by the capacitance. What is it?
Voltage.
Which voltage? The initial voltage, because I use the initial charge, right? So this is VC initial. So that's my voltage across the capacitor. We said that should go to 0. Now we know the function. The voltage across the capacitor as a function of time starts off at some initial value and then dies like an exponential like all the rest of them. Remember that these two graphs right here, they have to be in lockstep, right? If as goes the charge on the capacitor, so goes the voltage across it. So if the charge across the capacitor, or the charge on each plate, dies, then the voltage that they make will die. So this gives you a little bit of a sense of how you might find the other functions. For instance, I can go and I can say voltage across the resistor as a function of time will be the current as a function of time times R. So that's just using Ohm's law, but now putting in our functions. As goes the current, so goes the voltage, and vice versa. The whole point of Ohm's law is those two are tied together in lockstep. So if I go ahead and I put in my current function, which I also gave you, all I have to do is multiply that by R, and I have my voltage function. Again, I might group it so it looks like this. Put all the constants together. And then what is that quantity in parentheses? What is it? Voltage across the resistor at what time? Initial. VR initial. So my voltage across the resistor function looks like that. So, again, it's one of the same exponentials. Basically, these all go to 0, and I'm basically finding the functions at which they do that. They're all going to be exponentials. And in fact, I already pointed out that in this particular circuit, this initial voltage and this initial voltage are the same thing. So what I've really arrived at looks like this. I might, just to be a little bit more generic, might just describe this as the voltage graph. I might describe this as the voltage drop across AB, which could be either the capacitor or the resistor. And it just dies off with time. All right? The only little twist in this, if you might wonder, are they all going to be just the initial value times the exponential? The only little twist that you have to be aware of is that for these two functions, there is a square. So in that case, just a little bit more complicated. For instance, P as a function of time is going to be I as a function of time squared times R. So if you work this out, I guess I'll go ahead and just write down the answer. There is an extra 2 in there. That comes from the square. So that changes a little bit what happens with your benchmarks. So at t equals tau, the power is not, so it does not equal the initial power over E, or initial power over 37% of its initial, okay? So it does not equal that because of that extra 2. You can, of course, work out what it is. But other than that, it still looks the same. the power still dies off. You dissipate the most energy in the resistor versus time at the beginning. And likewise for the potential energy. You store the most potential energy in the capacitor over time, and then it does die off until there's nothing left to store. So that right there is the discharging circuit. Everything is an exponential. Everything dies to zero eventually. For everything besides the power and potential energy, which have those square things in them, everything dies off exponentially in a specific way. After t equals tau, you're at your 37%, 63% benchmark. Are there any questions on this circuit before I do the charging circuit?
Just wondering,
Yeah.
when you write it out, is it a minus t or a minus positive?
Where is it?